So now we are going to solve a problem which can be very relevant to the GATE exam. So we are going to solve a problem in which there will be the phase change involved. Generally, there is some confusion in the people who have not seen this type of question. So let us go through the problem. The problem is it is required to melt 5 tons per hour of iron. Now we are talking about the melting of iron and it is 5 tons per hour from a charge at 25 degrees Celsius to molten metal at 1600 degrees Celsius. So we have the initial charge, that is the iron is at 25 degrees Celsius, and we have to melt it, the molten metal at 1600 degrees Celsius. The melting point is given to be this 1535 degrees Celsius. The latent heat of fusion means melting. The latent heat is given to be 280 kilojoule per kilogram. Specific heat, so initially it is in the solid state, specific heat is 0.5 kilojoule per kilogram Kelvin, and in the liquid state it is 0.535 kilojoule per kilogram Kelvin. So we have an electric furnace that is having a 65% efficiency. Now how the melting is being done? We will supply energy through an electric furnace. Electric furnace will convert the electrical energy into the thermal energy that will melt the iron, and find the kilowatt rating. So we have to find out how much electricity we need to supply. Kitni electricity we have to supply. If now in the second part they have asked if the density of the molten state is 7000 kilogram per meter cube. So this is the density of the molten iron which they have given. This is the density, and bath volume. Bath volume is the volume where the melting is taking place is 3 times the hourly melting rate. So we have the bath volume, that means where we will melt it, that is 3 times the hourly melting rate. Whatever we are melting in an hour, the capacity should be 3 times of that. And find the dimensions of the cylindrical furnace if the length to diameter ratio is 2. So that means we have a cylindrical furnace in which the melting is taking place, and whatever is the melting rate per hour, the volume of the cylinder should be 3 times of that. Fine. So now let us first of all try to understand that if 1 kilogram of iron melts, how much heat we should give to the iron for the starting condition till the melting and whatever temperature we want the iron to be finally. So if we see the condition of the iron, so we can see from here that initially we have the iron at 25 degrees Celsius. So we have 25 degrees Celsius of solid iron. So this will be solid. Then from 25 degrees Celsius it will change, the heat addition will change it to melting point is 1535. So it will melt at 1535 degrees Celsius. This is the melting point. It will still be a solid. At this condition, if you heat it from here to here at this condition, let us say it is still the solid. Further, if you supply heat, this is the melting temperature. At the constant temperature, solid to liquid transition will take place. So we will have 1535 to 1535 degrees Celsius, but this is solid to liquid. The melting will take place. Then further 1535 to 1600 degrees Celsius, further temperature rise will take place. That is at what condition we want the iron to be. So 1600 degrees Celsius is the liquid. This is the condition we want finally the iron to be. Now let us see per kg how much energy is required. So if we have to find out per kg, if we have to find out per kilogram, so we can say this will be equal to m mass is the heat required, Q will be equal to m mass, we are talking about 1 kilogram. So m into specific heat C. specific heat solid to solid. So specific heat in the solid state into temperature change. Now see, the temperature is 1535 when the melting will begin, and initial temperature is 25 degrees Celsius. So from 25 to 1535, the temperature will increase. Final temperature is this, initial temperature is this. So we can write the temperature change 1535 minus the initial temperature is 25. The initial temperature is 25. So it will be this. Fine. Now let us see this here. We can say that the right. So we can say that further the melting will take place. So melting means latent heat will be involved. There will be involvement of the latent heat. So if we have the latent heat involvement, we have plus mass into latent heat. So mass we are taking it to be 1. So we have mass into the latent heat involved. If we want to find out per kg, so we will take m to be 1. We will take m to be 1. Specific heat in the solid state. So when the specific heat in the solid state is 0.5, this is the specific heat. So I will write it to be 0.5. Then mass into latent heat is given to us 280 kilojoule per kg. So this latent heat is 280 kilojoule per kg plus. Now we have 1535 to 1600 degrees Celsius. So again m into specific heat, now it has changed to liquid, so C liquid into dt, that is the temperature increment. So it will be 1600 minus 1535. So specific heat in the liquid state, this is going to be 0.535, and we have the mass, we have taken the mass to be 1. So we can find out the heat we need to supply for melting of 1 kg iron from the initial given condition to the final condition which we want. So heat Q required in terms of kilojoule per kg, and this is equal to, we can calculate the value for per kg. I have already calculated it. So let me just write this 0.5 into, we have 1535 minus 25 plus we have this 280 plus this is 0.535 into, we have 1600 minus 1535. So we have 1069.775 1069.775 kilojoule per kg. So this is the heat which is required to melt per kilogram of iron. Now, how much power rating we require? How much is the rate of heat supply that is required? So, rate of heat supply, the rate of heat supply required, let us say it is Q dot to melt, will be equal to rate of mass which we need to melt into the heat required per kilogram. So whatever is the kilojoule per second heat required, this will be equal to the number of kilograms per second you need to melt into the energy required in kilojoules to melt 1 kilogram. How much mass we need to melt? We need to melt the mass that is 5 tons. 5 tons we need to melt. So we will have 5 into 10 to the power 3. This much kilojoule, this much kilogram per second into small q, that is the heat required. So 1069 point, we have 775 kilojoule per kilogram. So we will get the this is actually in per hour. So we will have to divide it with 3600 because we have 5 into 10 to the power 3, that is 5 tons. This is the melting rate 5 tons per hour. Now, if we want per second, we have to convert it into the kilogram per second. That is why I am dividing it with 3600. So, we will get kilogram per second. Now, we will have the heat Q dot rate. This is the rate of heat that must be supplied to the Rn. So, we can calculate this. This will come out to be this into 5 into 1000 divided by 3600. So, it is 1485 point. This is 1485 point. We have 79798 kilowatt. This is the rate of heat supply which we need to give to the Rn. But we know that the electric furnace has to supply this heat. So, you need to supply power to the electric furnace. Suppose we are supplying the power to the electric furnace. Let us say power to electric furnace is W dot E, electrical power which you are supplying to the electric furnace. So, this is the power which you are supplying, and how much heat it is supplying? The electric furnace is supplying heat, that is equal to Q dot. So, we can say Q dot is the thermal energy it is supplying divided by W dot E, and this will be the efficiency of the furnace. So, we have been given, if we see here, we have been given that the electric furnace has 65% efficiency. So, 65% is the efficiency of the electric furnace. So, we can say whatever electrical work we are supplying, 65% of that it will supply or use it for melting of the iron. What will happen to the rest of the energy? It will get lost because of the high temperature of the furnace. That is what is the effectiveness that will not be utilized to melt the iron. Now, we can write the W dot E that is required. So, this will be equal to Q dot upon 0.65. So, obviously, whatever is the energy needed to melt the iron, we need to supply more than that, and we can calculate this. This will be divided by 0.65. We are getting 2285.84. So, we are getting 2285.844. So, this is the electrical power which we need to supply. This is one of the answer which they have asked. So, we have found out the electric power which we need to give. If an electric furnace has 65% efficiency, find the kilowatt rating. So, we have found out the kilowatt rating which we need to have for the furnace. Now, the second thing is, they are saying that if the density of molten state is 7000 kilogram per meter cube and the bath volume is 3 times the hourly melting rate. Now, what is the hourly melting rate? Hourly melting rate is 5 tons. So, how much mass we should be accommodating? So, how much is the volume which is melted per hour? Mass we know 5 tons, but what is the volume of that? 3 times of that volume will be the volume of the bath in which it is melting. So, let us find out the volume melting. Let us try to find out the volume melting, the volume melting per hour. So, volume melting per hour will be equal to, you can see that the density, we know density is equals to mass upon volume. So, volume if we want, we will have to write the mass upon density. So, this will be equal to m upon rho. This is the mass melting per hour. The amount of mass melting per hour. In 1 hour, how much mass is melting? That is this, and this is the density. This is the density of the melting mass. So, now we will have the mass melting, that is 5 tons. So, 5 tons means 5000 kilogram per hour. divided by the density. So density is how much? The density is given to be 7,000 kilogram per meter cube. So we have divided by, this is 7,000 kilogram per meter cube. So we will get the volume. Volume will come out to be, so we have this 5,000 divided by, this is 7,000. So it is 0.71428. 0.71428 meter cube. So this is the volume melting per hour. Now, what is the volume of the bath required? Volume of the bath required is 3 times of the melting rate per hour. So volume of the bath required, the volume of the bath required, so volume of the bath required will be equal to 3 times of this, whatever is the hourly melting rate. So we know the volume, so volume of the bath will be 0.3 into 71428. So we will have this will come out to be this into 3. So 2.1428. So 2.1428 meter cube. If you see, I am not doing any rounding off in between. So what is advisable is, in between at least 3 to 4 decimal places, you should continue writing your answer, because sometimes especially in the GATE exam, there is numerical ability type, numerical answer type problem, in which if you have rounded off in between, sometimes the values are such that we need to multiply with 1000, we will need to divide with 0.01. So whatever error you have made, that error will magnify. Suppose you have round off only 0.01, but in some steps of the problem, at one step you rounded off this much, like it was 300.01, you took it 300, fine. Let us suppose. So how much rounding off you have done? 0.01 you have rounded up. It seems to be very insignificant, but suppose in the problem, as you move forward, you have to multiply this number with 1000. So if we have to multiply whatever number was with 1000, the rounding off which you have done will lead to an error of 1020, and this is 3010. So rounding off will lead to an error value of 10 in the amount further in the problem. So that is why, if you want to round off the final answer, don't round off in between, at least 3 to 4. Whatever my experience is, the data, the amount of values which we have, 3 to 4 decimal places if you consider, that will be absolutely fine, right? So we have this much is the volume required. Now if we have this as the cylindrical bath, suppose we have this as the cylindrical bath, and let us say this is the length L, and let us say this is the diameter of the bath. This is the length L and this is the diameter, and it has been given in the problem. If we see, it has been given in the problem, the furnace, if we see, find the dimensions of the cylindrical furnace if the length to diameter ratio is 2. That means L by D is 2, that is length is twice of the diameter. So we can say, if we have this L by D is 2, so we can say L is equals to twice of diameter. So we can write it like this, twice of diameter, fine. So if this is the volume of the furnace, what will be the dimensions? So we can write the cylindrical volume. Volume of cylinder will be equal to pi by 4 d square, this is the area of the base, pi by 4 d square into the L, length of the cylinder, into L. So this is the volume, and this volume should be equal to 2.1428. Now we know L is equals to twice of D, so we can rearrange it, it will be pi by 2 d cube, and this will be equal to 2.1428, fine. So we can find out the value of D from here. So I will write this into this value into 2 and divided by pi and whole to the power, we have 1 divided by 3. So we have 1.109. D will be equal to 1.109 meters. So we have the value in meters because all the units we have solved in the SI units. Volume is in meter cube, so we'll get this in meter. And the length of the cylinder L will be equal to twice of this. So we have 1.109 into 2. So we have this as 1.109 into 2. So 2.218 meter. So we have 2.218 meter. So this is the answer of the second part which was asked. Not a very difficult problem, but yes, we can see if the phase change is involved, what we can write, how we can write. And also the purpose of this course is also to prepare us for the upcoming exam and to have in mind whatever questions we may be asked in the exam. So that is what we should cover. So this is the solution. I'll just move the screen once so that if you want to write down anything, you can comfortably write. So this is the screen here. I'll just slowly move it so that if somebody wants, you can pause the screen and you can write.